Greetings, happy coders. Welcome back to Pac-Hack, and this is the second part of the Pac-Man ZX Spectrum version hack, which we have already established where the maze is stored and the graphics for the maze, and managed to load that into AGDX where we can now edit the maze. So if you haven't seen that video, go back and watch that first. Yeah, so this is the original, as you can see here, and we'll switch over now to look at the AGD version that's in the editor. So as you will have seen from the previous video, we've loaded in the characters that are used in the game. Everything is done using effectively user-defined graphics, 8x8 blocks like this. So all of the characters in the game, the font, the Pac-Man, the animations, everything's done using this set of characters, and so therefore it means that we can edit them. Now, as was established again in the previous video, we don't need to do anything with the colors here. I've added the colors for the purpose of creating the map, but if we change the color of Pac-Man on here, for example, or anything like that, it's not going to affect the game at all, because basically that's drawn elsewhere, and I'm not going to worry about that. I'm not going to change the colors. The colors are more or less okay and not worth worrying about. But what you can see I've done is I've changed the font to use the arcade font here. We'll have to do a bit more work with this font because of, obviously, there are also things to do with score and printing and so on. But what we can see here is that we've got the there are two things here, ready and also the score here. And the reason for that is that, as I mentioned, the game is using the ROM to print the characters. So what the coder has done is, because the only text that's written during the game, when the game's actually in play, is this score and also this ready sign here. So what that basically means is that it allows the coder to display the score and this ready sign without switching to another character set, because otherwise, when you're doing the score and printing the Pac-Man running around and everything like that, you'd be jumping back and forth between two different character sets each time, and that wouldn't take up a huge amount of time. But since the coder had obviously got a little bit of spare memory here, then obviously that's what they decided to do, to make that work like that. And that's why we've got some of the font stored here, and then the rest of the time it uses just the regular system font. So again, another reason for this is that they're using the system font, obviously, is to save memory for a 16K game. But obviously we're working with 48K, and a bit later on we'll look at how we can change the font in the game so that it looks like the arcade version. Alright, so yeah, just a summary then. You've got the Pac-Man display, you've got the ghost eyes, you've got little scores that appear when you pick up bonuses or when you eat ghosts. You've got the regular sort of dots and the power pill here, which I've changed. It was a little bit bigger than that, and I've changed the fruits to look a little better. I mean, you know, I guess it's subjective, but I think they do look a bit more like the arcade. And the maze itself. Now, as you can see, the maze itself is drawn with only 1, 2, 3, 4, 5, 6, 14 different tiles, and I haven't checked, but I'm guessing, I'm going to guess that the tiles, each of these is going to obviously stop Pac-Man from moving, and that's probably done by checking if the tile number is between this number and this number. That's likely to be what happens, because they're all lined up here. But I haven't actually checked that, because there's no need for me to change that rule as long as I keep the tiles here. If I wanted to add more tiles, for example, or change the way that the tiles behaved, I might want to do that, but there's no real need here. But what I have done, though, is made the graphic a little bit thinner, because the double thickness, You know, if it was sort of like double thickness like this, which is what it was in the original release, it makes the maze look a little bit chunky, because obviously the maze is cut down size of the original arcade, and the original arcade would have had this double size, but obviously the sprites would be 16 by 16 instead of 8 by 8, so the ratio between Pac-Man and the maze graphic is now more similar to the actual arcade. So yeah, those are the only changes really, and that's the character set. All we'd have to do then to import this character set into the original game would be to save off a binary starting from this address here, which tells me the start address. We'd save off this 768 bytes, that's just pixel data, remember. The color data is done using an overlay. And we could load that into the game. In fact, we can do that right now, why not? So let's just take a look at that. Okay, so first of all, we'll just save the binary data. Bring that down so I can see 37360. Okay, we're going to load it in at 32000. That's the area of memory that we already established in the previous video, is where this graphic is stored in the game. For here, we're going to save it off at 37360. That's where it's stored in AGDX here, and it's 768 bytes. Like that. Let's switch over now to the Pac-Man game. Okay, so here we are in the original game. Let's load this binary data in. And we'll unpause the game. Okay, so as you can see, the maze now looks a little bit more like the arcade. The dots are in. Well, you know, everything's worked. The ghosts are slightly different. Incidentally, the ghosts in this game, there are only 2 frames. So what I've done is made a very simple animation that will work in any direction, and it just has the ghost's eyes moving left to right and wobbling a little bit. And I think it does look a little bit more like the arcade. Obviously, there's not too much you can do. Another interesting point here is, if you take a look at the score, you can see what's happening here. That this section is pre-written using the ROM font, and that part and this part here never changes in play. You can also see that there is an extra 0 here that's not drawn, and so basically, because the score is only ever done in increments of 10, there's no need to add the score in terms of tens. You can add the score using only 5 characters, and that makes it a lot easier, because, for example, if you want to add, say, 1600 points, well, now you only need to add 160 points, and that's important because 160 is an 8-bit number, so it's going to be easier to add the score than adding a 16-bit number, which is slower and a little more complicated to do. So that's a good way of keeping the number down. Gives the impression of adding 800 or 1600, but in fact it's only adding 80 or 160 and then displaying it. And changing this font has helped us to notice that that's the way that it's done. So that's quite interesting as well. Okay, so that's the graphic in there. Now let's go back and take a look at how we can alter this maze. Okay, so here we are back in AGDX, and this is the original data loaded in from the game, and as you can see, it's a full screen maze. It also includes, interestingly, the Pac-Man here and also the ghosts, but as it turns out, there's no need for those to be stored there, so I haven't bothered to do that. Now, the first maze, which was suggested by Stuart, was this one, which is more similar to the arcade, and it works around one of the initial problems that we're going to have, which is this exit here, because the game is going to check for the exits here and here, and that keeps the exits in the same position. But obviously the problem with that is that this exit tunnel is going to be huge, and it's definitely not going to feel like the arcade. So that's probably not ideal. So then I moved on to another maze, which was this one. Well, it wasn't exactly this one. Basically, there was another one which I made even narrower, which didn't have this gap in the middle, so that it looked exactly like the original. But that created another problem, and that is that the ghost house here, if we go back here, you'll see the ghosts are all inside the maze here. And in the original Pac-Man arcade, 3 of the ghosts are in the house, but the red ghost actually starts outside. Now, I wanted to do that originally, but what I discovered was that each ghost has its own initiation routine, and this ghost here, when you put it here, it tries to it should go to here rather. When you put it here, it tries to initiate itself by going up, but of course it can't go up and it just gets stuck. So the whole thing just didn't work. Now obviously, when you're doing a kind of hack like this, if you really want to do it perfectly, you could go back, change the code, edit it, disassemble, and so on. But I didn't feel that was really necessary, and instead I just did a workaround where I added 1 column to the maze here, and then we have 1, 2, 3, 4. We can fit 4 ghosts into there. So it's not arcade perfect, but in terms of how it plays, the feel of the game doesn't change that much, because the red ghost, he jumps out straight away as soon as the game starts and jumps up to this position. So it more or less starts in the same way that it would if you did that. But if you only had 3 spaces here and you put one of the ghosts overlapping on another one, it also didn't work. So some kind of issue with it overlapping wouldn't allow the ghost to initiate. They all had to have their own separate little space, so that was the reason that I went for that. Okay, so we can think about the potential issues that we might have with a maze like this, and probably the best thing to do is to load this into the game and show you what possible issues there might be. So remember, there are two parts to this. The first part is to load the pixel data into the correct place, and the second part will be to load the color data. So I'll load the pixel data first, and then that will show you how it might look, but using the original color data, and then we'll load the color data in, and at that point we should have a map which looks correct. It's worth bearing in mind here that when you're making changes like this, obviously you can cause the whole game to crash. So if you are working on a hack and you're sort of adding things step by step, it's always good to keep saving copies as you work along. And we'll jump back into here. We're going to save a binary here. Now we've already established where this is stored, so we'll save it as map edit here. It was at 25056, that was in the previous video. So we'll save that off, and as you may recall, 64768, and it's 704 bytes because we don't have these 2 rows like that. Okay, and the color data, as you'll remember, is literally, we're just going to save the color data from the actual screen itself. So I'm going to go into this mode, which is query mode here. The reason for that is that it will remove the cursor, so that this shows the map exactly as it is. We don't want that. We don't want a flashing cursor as part of our color data. So yeah, and as you remember, it's 22528 is the start, so we add 32 to that, which gives us 22560. And we can now save off the overlay here, and that's 25824 is where we'll load it into the game. But 22560 is actual screen memory here in terms of attributes, and that's also 704, like so. Okay, so let's now switch back over to the main game. Okay, so I'm back here waiting for the game to start, and now we're going to load our binary data in. So we'll load this one in at 25056. And we'll load this one in at 25824. Like that. Okay. If we start the game now, let's see what happens. Okay, so pausing the game here, and so far so good. It looks right. The colors are good. Everything is fine. Let's see what happens when the game moves in. Okay, so we've immediately got a problem because the ghosts here are obviously not starting in the right places. And furthermore, as you'll see, basically it's possible it doesn't exit from the right to the left, but we can do a couple of little tests here just to see what happens, because okay, so what I did there, I just wanted to test what would happen if I went off the side of the screen here and here, and what I can see is that it doesn't matter where you go off the side here or here, it will reset to the other side of the screen. It'll roll over back to the other side. So that just tells me that there's some kind of simple check going on, which you would imagine to be the case, that it checks here, which is probably 0. Well, it probably checks if it goes over a certain number here, and if it goes from 0, this will be 0, so probably to 255. If it hits 255, then it probably realizes it's gone off the screen, and then it makes it reappear over here. Now what we do know from this game is that it uses the ROM to print all the characters, which means that we're going to be working with rows and columns throughout. So that should make it fairly easy for us to identify where the tests are taking place for the ghosts, where the ghosts begin, and also to test what happens when we go from the left to the right, and hopefully change it. So let's do those kind of things one step at a time. And the first thing I want to do is get the ghosts all back in the house at the beginning. And to do that, we're going to have to do a little bit of poking around to try to see if we can figure out where the ghosts are and what exactly they're up to. So let's do that now. Okay, so we want to try now to find out where the ghost data, where the X and Y coordinates of the ghost are held, because we can be fairly sure, because we know that it's being printed using a ROM routine, that it is going to be using a line and column routine, and so therefore the ghosts will each need to have their own line and column. And what we do know is, I'm going to work with columns here, what we do know is that the ghosts start, as you can see from here, AGD tells me the column here, and this is 11, so we know that it's 11 and 14 is going to be our X coordinate. So let's take a look and see what happens when the red ghost moves and jumps out here, because once it moves up and it gets to here, then instead of 11 it will be at 9. So we're going to look for somewhere in memory that starts at 11 and then changes to 9, and hopefully that's going to give us our first indication as to where the ghost is actually stored. Okay, so here we are in the game. So I pause the game here, and we can see that the red ghost has already moved up one space. So I'm now going to go to the poke finder, and I'm going to reset it here, and we know that this started at 11, so this now is at 10. So using a poke finder in Fuse, we're going to search for the value 10, and we'll now move it forward, move the action forward, pause it again, And let's just do a little count. So this was 11, this was 10, this was 9, 8, and it's now at 7. So we'll now look for the same value that was originally at 10 that's now at 7. And you can see immediately that it tells us there is only one value, which is this one here. Now this is page 5, which for the 1 to 8K spectrum, this means it's in the first 16K of RAM, which obviously we know that it would be because it's a 16K game. Plus the this is the offset here. So in order to calculate the address, we just need to bring in a calculator like this, and that's the first 16K. That's the start of the RAM. So we'll put that into hex, and we're going to add 27F5 to that, which gives us this address here. And if we look at that one in, so it's 26613. So now what we'll do is we'll poke this 26613 with another value. So let's say that we poke it with something like 13, and that would immediately put the red ghost down here if what we believe is correct. Okay, so let's poke the memory. 26613, 13, like that. Press OK. Okay, and you can see immediately what happened there was that and it's quite interesting, because what happened is that the ghost was then printed here, and it then moved and carried on, and you'll see that the restoration piece here, which is what this one here is under, was also printed here, and that's why we're left with a residual sprite here, which obviously originally would have been this dot here. So we now know that the horizontal coordinate for the red ghost is stored at 26613, and this is address 67F5. Okay, so what I'll do is I'm going to reset though. Okay, so go back to the memory browser now. Take another look at this. Okay, so this is a little more like it. So 0, 1, 2, 3, 0, 1, 2, 3, 4, 5. So 0E, 0, 9. So this one we know is the row. Now, could this one be the column? I suspect it probably is. So 0E in hex, of course, is 14. If we look here, we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, exactly 14. So we could be pretty sure that that 0E is the address for that ghost. And if we look at the rest of the coordinates here, we're looking 67F. Difficult to say. We're going to have to try and figure out where the rest of the ghosts are, but it would be very strange if they weren't all stored together. What it might be is that these numbers here are additional information about the ghost, and you know, things like its status, is it running away, or what direction is it moving in, something like this. That's probably what that is, and it may also hold the tile that it previously went past over. That might be another possibility. None of that which we need to really worry about, but what I'm immediately noticing here is that we've got 0E here, we've got a little bit of data here, and then we've got OCOB followed by some similar data, and then we've got another 2 here with similar data, and then something again here like that. So again, it's maybe this is the hacker's eye, I'm not sure, but I can see very clearly in the code that we've got these 2 points here and these 2 here, which are kind of standing out for me because they look like coordinates. they're low numbers, but you see we wouldn't have 0 1s or zeros for coordinates because those would be way off the screen here, so that's likely to be data. And if we look at OC, OB, then we know that OC is basically 12 and OB is 11. And of course, if we look at that, we could see that we know this one's 14, so that one we know this is 11, and we can be pretty sure that that's that green ghost, because that ghost is basically at OC, OB, 11, 12. 11 is this one, and 12 is this one here. Okay, sorry, 11 is this one is 12. Yeah. Okay, so I'm pretty sure now that those ghosts, that data for the ghosts is held here, and we've got a gap of, it looks like, is it 8 bytes? I'm not sure. Let me just check. So we know this is the first ghost, and if we go 1, so 1, 2, 3, 4, 5, 6, 7. Yeah, it looks like it uses 8 bytes of data. I don't know what this data is for. I'm not going to worry about it right now because it doesn't really concern me. It could be something to do with color as well, perhaps. I don't know. Right, so that is all very well, but in the game we don't really need to know about where the ghosts are, because we're not going to have to move them in game. What we do want to know though is when that address is first written to, because that's going to tell us where the ghosts actually start from at the beginning of the game. So that's the next thing to look for. So I'm going to load our original back in again one more time. And I'm now going to go to the debugger, which you remember again from the previous video. If you haven't seen it, go back and watch it. The debugger is going to allow us to set a breakpoint for when a value is written to. So I want to say break when writing to 26613. Okay, let's put that in there like that. And so we're going to look at this to see when the game starts, and basically what I'm thinking here is the game will start and it will set the ghost to be at that position where it should begin. So we'll see what happens when we start the game now. Okay, so immediately it's gone into the game, and what you can see is that we've got here this command here, LDIR. Now, if you don't know assembly, I'll explain. Basically, what this is doing a byte copy. So you can see here, this is the start address. This is where it's copying to, and this is how many bytes to copy. Okay, so if you look at 2E, how many bytes is it copying? The total is 2E, which is 46 bytes. So that tells me that there are 4 ghosts, and it's probably copying 11 bytes per ghost, unless perhaps it's also copying some additional data to do with Pac-Man or something like that. I don't know. But what we do know is that you can now see that 67FO is where the ghost data is stored in terms of its original position, because, for example, 67F5 is the red ghost's coordinate. And so what we now know is that that's the start of the data. And we also can see here 67CO, this is where the data is being copied. In other words, 67CO contains the data for the initial start position of the ghosts. So by that reckoning, 67F5 holds the ghosts row, doesn't it? We've calculated. So 67C5 would contain the row that the red ghost should start at. So 67C5. 67C5, sorry, switch to hex. 67C5 is 26565. Right. So I'm gonna now delete this break, close it here. I'm reload our game back in, and now I'm going to poke this value here, machine poke memory. So our value was 26565, and let's poke it with a value of, say, 13, because we know that that's just below the maze. So what should happen now, you should ask yourself. As you can see right there, the ghost started at row, should I say, 13. So that basically means now that we know where that ghost begins in terms of its column and its row, and we can basically poke that into where we want. So we go back to the AGD editor, and basically we just poke, we look at the values here. We've got 14, 11, 15, 11, 16, 11, 17, 11 there. So looking back at the memory browser, you can see here 67CO. This is our red ghost here. This is our green ghost here. And these are the other two. And you can see B, B, B. That's all row 11. We don't need to change row 11. So the only values that we need to poke here then are the we need to poke this one back to 11, obviously, 67C5. And then we just need to poke these ones, this one, and the other two to line them all up. Okay, so I'll just do the calculations, and we'll make those pokes now. Okay, so the first thing I'll do then is I'll cancel this poke, because it's actually, the red one is in the correct place really. It starts here, and that's where we want it to start. We'll, I think, perhaps move it across one space, so that the green one, so we'll have the yellow one here, the purple one, the red one, then the green one here, or vice versa. It doesn't really matter, does it? I think we'll put the red one there. So what I normally do when I'm working things like this, when I'm dealing with a set of different pokes, is that I use OpenOffice, and it has a quite nice little function for converting hex into decimal. So over here I've written down the locations that I've worked out are the locations of the ghosts, as we saw, and here it uses a function called hex to dec, and this gives me the decimal version of the hexadecimal code over here. And we're not going to change the row. We know that the rows are all the same. It's all the ghosts are on one row. So all we have to do then is change these four numbers. And as you can see here, that's the numbers that we're going to poke them to. So if I just move that across, what I can do then is I can just take a copy here, go to the poke memory, paste that into there, put the value that I want into there like that, and same again, like so. Now we do the magenta one, and actually, well, that doesn't matter, we've put one in the wrong place there, 16. So this one should be 16. It doesn't matter if the purple and the magenta one are in a different location, does it? Okay, so this is our default position for the ghost. So all we have to do now is test it. And as you can see here, very nicely, we have the ghosts all starting in their positions, and obviously the yellow one and the purple one are reversed, but I don't think that's really going to make any difference. So yeah, that's our first problem solved. We've got the ghosts sorted out. Okay, so I think we'll leave it there for this episode. There's still plenty to do. We need to think about the maze exits. We need to think about the number of dots, which has changed, the flashing of the power pills, and the font as well. So there's a few more things to do. I hope you found this series interesting so far. It is quite in-depth and lengthy, but it's the kind of thing I personally would enjoy watching, so I thought I would make a couple of videos and see what kind of feedback I got. If you do like it, then remember to like and subscribe, and do leave your comments below to let me know what you think. If you'd like me to make the episodes a little bit more compact and punchier, then I'd be happy to do that. But as I said, I quite like doing these sort of longer versions, just so that you can see step by step, and you might even want to try some of these things yourself. Okay, so as always, keep enjoying the spectrum and happy coding. Thanks a lot. Bye bye. This video would not be possible without the amazing contributions from the people whose names you can see scrolling up the screen right now. If you'd like to be one of them, you can get all my games for free. You can get some coding tips. You can even get to dictate which games I work on in the future, and you might even feature in them. So if that sounds good to you, then head over to the Patreon page. The link is just coming up now. And in the meantime, happy coding. Bye bye.